In this video, we're going to take a look at our last major integration technique called partial fractions. And you may have seen partial fraction decomposition done in a previous class in, say, like college algebra or something like that. And you'll see it again when you get to differential equations if you take that class. It's another sort of difficult and tricky technique, and I want to kind of guide you through it here. So the idea is that partial fraction integration allows for integration of complex rational functions. So this allows for the integration of complicated rational functions. And just as a quick reminder, a rational function is basically a function that's made up of a ratio, hence the word rational, of polynomials. So one big ugly polynomial over another big ugly polynomial. And the idea is we're basically going to be doing reverse finding a common denominator. So the idea is if you have, so let me write that down. It's the reverse of finding a common denominator. So if I give you two fractions, here's 3 over x plus 1, that's not too bad. Here's another one, minus 2 over x minus 2. So here's two separate rational functions. Normally we would want to try to simplify this and combine them into a single term. And to do that, we would need to find our common denominator. And I'd notice the common denominator in this case is going to be an x minus 2 times an x plus 1. And so this fraction over here needs to be multiplied by 1, but that special form of the 1 that's x minus 2 over x minus 2. And similarly, this one needs to be multiplied by x plus 1 over x plus 1. So we would write this as 3 over x plus 1, but I'd multiply that by x minus 2 over x minus 2. Let me just add some parentheses around that part as well. And then I would subtract 2 over x minus 2 from that, and I'd have to multiply that by x plus 1 over x plus 1. And again, put parentheses in all the useful places. And if we distribute through and start combining like terms, so let me just distribute through. Here we'll get 3x minus 6. Let me do a big fraction on the bottom. We're going to have that product x plus 1 times x minus 2. And we'll FOIL that out in just a minute. But so far I've done this distribution. Now I want to take the minus sign into account and do the second distribution. So we'll get minus 2x minus 2. And if we simplify the numerator by combining like terms, I have 3x and a minus 2x, which leaves me with just an x. And I have a minus 6 and a minus 2 for a grand total of minus 8. And then on the denominator, when I FOIL this out, I'll get x squared minus 2x plus x minus 2. So I'll get x squared minus 2x plus x minus 2. And what it ultimately simplifies all the way to, again, collecting like terms on the bottom, is x squared minus x minus 2. And so it turns out that this is totally equivalent to this. Those two mathematical expressions are equivalent. One is made up of two relatively simple rational functions, and one is one big complicated rational function. When we do partial fraction decomposition, the idea is we may encounter something that looks like this more complicated version over here, and we want to integrate that. This is not something that I know how to integrate, but if we can break it down into two simpler looking pieces, these are things that I would be able to integrate. They're going to be, each of these would be integrable using basically a U substitution. And so it wouldn't be too bad at that point. So normally we go from here to here, but in this case, we're going to want to go in the reverse direction. And so how do we do that? Let's think about it kind of hypothetically in a more general case. So if we know that we have a complicated fraction, and if our function f of x looks like a rational function, so we have maybe some p of x in the numerator over some q of x in the denominator, it's the ratio of these two functions, then what we want to do is to factor. So if we think about the order that we went in on this problem, if we were going backwards, the first thing I would want to do is take this denominator and factor it into these two separate pieces. And you'll notice that these two separate factors wind up being the two separate pieces in our two separate rational functions that we wind up with. So that's going to be our first step. We're going to want to factor this q of x. As much as possible. This assumes that basically the order of the numerator is less than the order of the denominator. If, on the other hand, we had like a cubic on top and a square on the bottom, you would actually want to do some sort of either long division or synthetic division to try to simplify the whole thing, and it might just turn into a nice polynomial. So part of the assumption is that kind of the denominator is the part that looks worse. The denominator looks worse than the numerator in this case. And this will work in other cases as well, but that's really the type of problem you want to deal with this on. Okay, so once we've got q of x factored, it turns out that once we get, and so this is going to kind of seem complicated. I'm going to give you some rules, and then it's really a matter of doing a bunch of actual problems. In this hypothetical sense, I'll give you the rules, but again, we want to actually do problems. Okay, so for each linear factor that we get, of q of x, so in our case, in the example above, they were both just linear factors. There were two of them, and they were each of what we call multiplicity 1. They each only occurred once. But for each linear factor of q of x, it may take the form of the following. So of the form ax plus b, there's the linear part, and it may be raised to some power n. And that's going to be the multiplicity of that, basically how many times that factor shows up. But for each one of these, the partial fraction decomposition must include the following terms. And so we'll write this all out, we'll do some examples, and I'll try to hopefully maybe like kind of come back and summarize some stuff at the end. So the partial fraction decomposition needs to have some initial constant over ax plus b to the first power plus a second factor over ax plus b squared plus another factor over the cube. I'll write that out. Oops. Back to lower cases. Plus dot 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 all the way up to an an term where n is the multiplicity. So in our case, if the multiplicity is just 1, if n is 1, I can ignore all of these terms. So we'd ignore if n was equal to 1. So if all of our terms only have multiplicity 1, then we don't need to have all these extra terms. And this would be one basically term that we need to include. For each, what we're going to call quadratic factor, so this is the linear factors. For each quadratic factor, so we may wind up with a quadratic that can't be factored and simplified anymore. So for each quadratic factor, of the form, it would look like ax squared plus bx plus c raised to the power n. The partial fraction decomposition must include basically a term that looks like this. So you guess linear terms on top. A1x plus b1 over that quadratic factor ax squared plus bx plus c, plus a second one, a 2x plus b2 over that same ax squared plus bx plus c, now squared, plus, so we're following the same pattern as before, but now instead of guessing just a constant on the top, we're now guessing a linear function on the top and increasing powers of the quadratic term on the bottom. So again, increasing multiplicities, plus dot dot dot, all the way up to an nth one of these terms, again, if the multiplicity of that quadratic term is of multiplicity n, if it shows up a bunch of times. Okay, so this looks awful, and quite frankly, it is awful, but again, we can ignore all of these if n is equal to 1, so if it's only of multiplicity 1, we can ignore all of those. So this is kind of a general approach. There's other ways to think about this. You may have learned this another way if you've seen this before. If not, it's going to make more sense once we do some examples. So let's just jump in and actually do some examples, and I'll try to highlight what I'm talking about as we go through these problems. I got at least 3 or 4 examples here, so let's take a look. Okay, so again, this is sort of the approach that we're going to take. These are our rules, in a sense. But all you need to remember is basically when the factor is a linear factor, you just guess a constant. When the factor is a quadratic factor, you guess a line. You always guess on the top a numerator that's basically one order below whatever's on the bottom. And you forget about these extra multiplicities. The multiplicities, we just need to account for those. If there is a higher multiplicity than 1, we just need to add in additional terms. Okay, so let me just do an example. Let's stop talking about it and actually do it. Okay, so let's say I want the integral of 1 over 4x squared minus 1 dx. So the first step is to try to factor this denominator. And hopefully we recognize right away that this is a difference of 2 perfect squares. So this is going to be a difference of squares. So again, start by, in fact, I guess I'll just do that as the next line. So start by factoring the denominator. And what we'll find is our integral is going to be the integral of 1 over, in this case, 2x plus 1 times 2x minus 1 dx. And so going back up to our rules, which of these rules is being satisfied? Well, in this case, we have 2 different terms on the denominator. They are different, right? This has a plus, this has a minus, and each of them only occurs once, so they each have multiplicity 1. So we have 2 different distinct linear terms. That means we're going to have 2 different terms that wind up looking like this, because again, the multiplicity is just 1 for each of these terms. You can think of this as being a first power tucked in on either of those. So I'm going to erase those because we don't want to write those explicitly necessarily. But this is what our problem looks like. So we want to rewrite the whole integrand, the whole piece that we're going to integrate. And the form that we're going to do it is, again, up here, we used A's with subscripts A1, A2, A3, and so on. You're welcome to use subscripts if you'd prefer, but you're also welcome to just use different letters. I could just call this like capital A, capital B, and so on for these various problems. So the idea is I want to figure out how I can rewrite this piece, not as a single fraction, but as two different fractions. So the first fraction I want to be over the 2x plus 1 term, and the second fraction I want it to be over the 2x minus 1 term. And what needs to go in the numerators? Well, they're both linear factors of, in this case, of multiplicity 1. So we just need a constant on top. So I'll guess a over here, and we could guess b over here if you wanted to call this a1 and a2, or however you want to do it. I tend to use completely different letters, and maybe I would use, if it starts to get really nasty and we have a ton of these, then maybe I'll start to use subscripts. But if I've only got 2 letters, let's just use 2 different letters. So our goal is to figure out what the A and the B need to be so that when I found the common denominator of these two and combine them into a single fraction, I would get the fraction that we've got over here. So what do the two numerators have to be so that when I combine this into a single fraction by finding a common denominator, that this is what I would get? Well, we can just go through that process. So basically just start to find a common denominator. For the first one, I'm going to need to multiply top and bottom by this denominator over here. So it's going to be a over, oops, that's an ugly a over 2x plus 1 times 2x minus 1, 2x minus 1 over 2x minus 1. And for the second one, it's going to be b over 2x minus 1. Let me toss extra parentheses around these. And I'd multiply top and bottom by this denominator. So 2x plus 1 over 2x plus 1. We can FOIL out the bottom if we want to, but there's absolutely no reason to. I know clearly that these denominators match this denominator over here. So far we're good. I've got this denominator, and the denominators are the exact same thing on the right-hand side as well. So for this big expression that we've got here to be equivalent to this expression over here, the denominators are already the same. I just need the numerators to match up. So we really only need to look at the numerators. I hope that makes sense. So all I'm suggesting is that the denominator of this side already matches the denominator of this side. You could think of combining these into one single fraction if you wanted to, right? You would just add the two numerators together over this bottom number. So we really only need to worry about the numerators. The denominators are already the same on both sides. So we just need to force the numerators to also be the same on both sides. And when we do that, we wind up with a 1 on the left-hand side, right? That was the numerator we started with. And on the right-hand side, I'll have a times 2x minus 1 plus b times 2x plus 1. This is the numerator I would get if I were to combine these pieces, these two pieces over here, into a single fraction. Okay, so it looks like one equation for two unknowns, but the reality is it's kind of two separate equations. So it looks like one equation for two unknowns, right? We're trying to find A and B. So we have two unknowns, but really only one equation. It's really two equations. And how so, right? I only have one equal sign here. It's written as one equation, but there's two separate pieces of information encoded within this. if this side is going to be equal to this side, and these terms involve both constant and terms proportional to x, so basically x to the first power and x to the 0th power terms, I need the constants on this side to match the constants on this side, and I need the x terms on this side to match the x terms on this side. There's really two separate pieces. So what I'm suggesting is if ax plus b is equal to cx plus d, even though it looks like I've only got one equation, there's really two. I know that a and c have to be the same thing, but I also know that b and d have to be the same thing. Here's one equation I can set by forcing those to be equal, and a second equation comes from by forcing those to be equal. And we've got the same thing over here. It's just written out a little bit messier right now. So I'm going to delete this. But that's the idea. It's really two equations. One for the x terms and one for the constants. And if this was quadratic, we would have three different terms because we'd have the x squared terms, the x terms, and the constants. So basically, when you're setting two polynomials equivalent to one another, every single coefficient has to be equal for the two polynomials to be equivalent. So that means the constants, the x's, the x squareds, x cubes, x to the fourth, and so on, all those terms would have to be equivalent if the two polynomials are equivalent. Okay, so I'm going to break this up into those two equations. And the way that I like to do it is using this notation. You may have seen this before, you may not have, sometimes called big O notation. And I'm going to look at all of the order 1 terms. You could also think of that as all of the order x to the 0th power terms. These are all the constants. So this is a capital letter O, and it just means things that are on the order of 1. So things that are on the order of a constant. We will also look at all the things that are of order x, essentially, or order x to the first power. So you could think of it as either one of these, whichever one you want to write. And in this case, I'll stop writing both of these going forward. I'll probably just write order 1 and order x, or I'll just write order x to the 0 and order x to the first, and so on. But what are the constants? If I look at these two equations, on the left, the constant is a 1. And on the right, the constant is going to be, I'll have a negative a when I distribute that a through. So I'll have a negative a. And I will have as a second piece a plus b. Right, so the constant terms are basically this term and this term. And that's what gives me, once we multiply through by the a and the b, it gives me those two terms. So just keep that in mind. Let me not make this too messy. Now let's look at the order x term. So what is the order x term on this side? There is no order x term. If we want to, we can artificially put one in and write it as 0x plus 1. So really I have 0 x's on the left. How many x's do I have on the right? Well, I have, multiplying this through, I'll have 2a of them. So I'll have 2ax plus 2bx. So these are all the terms that are proportional to x on both sides. I have a 0 times x is equal to 2a times x plus 2b times x. And I'm just basically pulling the x out of it, canceling the x on both sides. So here are the two separate equations that we have. And this is perfect because now I have two equations for two unknowns. So we have the exact right number of equations to uniquely solve for the number of unknowns that we're dealing with. So there's different ways we can do this. You've hopefully solved simple linear systems like this before. This is, for a lot of people, the hard part, and this is something you'll do eventually if you take linear algebra. That's kind of one of the main focuses of that class, is solving linear systems of equations. But we have a substitution method where I can solve one of the equations for one variable and plug that into the other equation. Or we have the elimination method, where I can try to combine the two equations together in some way, basically add this one and this one in some manner to eliminate a term. And it really, in this case, is kind of 6 of one, half a dozen of the other, whatever your preference is. So maybe in this one, I will do a substitution method. And maybe, actually, this one's easy. Let's do the elimination method on this one. And I can do a substitution method on the next one, but both are going to be easy in this case. So if I were to take the top equation and multiply every single term by 2, so 2 times this, and then I were to add them. So add 2 of the top equations, basically multiply it by 2 and add it to the bottom equation. What we would see is, so let me erase all of this. And then we'll do it cleanly in one spot. Okay, so what I'm suggesting is, if we do the elimination method, and maybe we'll just do it really quickly both ways. If we do the elimination method, I want to get one of the coefficients to match. So the eliminations method is ideal when the coefficients already match or they're opposites of one another. So I'm going to change the top equation. I'm going to multiply every term by 2. So I'm going to be getting 2 equals negative 2a plus 2b. And on the bottom, I'm not going to touch it. It's going to be 0 equals 2a plus 2b. And now I'm just going to add these. And when we add them, on the left we'll get 2. On the right, when I take negative 2a and I add positive 2a, I'll get 0a. So that term's gone. And when I add the ones on the right, I'll get 4b. And now this term is basically gone. We can ignore it. And I have a single equation for b. And all I need to do is divide both sides by 4. And I'll get that 2 over 4 is equal to b. Or simplifying it, b equals a half. And once I have that b is equal to a half, I can go back and plug into either of the original equations to solve for what the other one must be. So now plug into one of the original equations. And it doesn't matter which one. Pick whichever one you think is going to be easier. And I'll get 0 equals 2a plus 2 times a half. And 2 times a half is just going to be 1. So we've got 0 equals 2a plus 1. I'll subtract 1 from both sides, and I'll get negative 1 equals 2a. Divide both sides by 2, and I will get a equals negative 1/2. And so there are the 2 terms that I was looking for. If we do the substitution method instead, so again, in the substitution, in the elimination method, we try to make the coefficients of one of the terms be either the same or opposite, so we can either add or subtract the 2 equations from another. In the substitution method, I use one equation to solve for one variable in terms of the other and then plug that into the other equation. So in the substitution method, I'm going to start with 0 equals 2a plus 2b. And I'm going to use that to solve for one of the variables. So I'm just going to subtract one of them over to the other side. So in this case, I'll say that 2a, maybe I subtract 2b over to the other side. We could also just divide by 2 as our first thing. Maybe that would be the easiest way to do it. So you can do this in either order. I'm going to just divide both sides by 2. And so now I've got 0 equals a plus b. And now I'm going to subtract 1 over to the other side. And I will get that a is equal to negative b. And I want to plug this into the other equation, whichever one I didn't use. So I'm going to plug that into the other equation. The other equation is 1 equals negative a plus b. So I'm going to substitute everywhere that a shows up. I'm going to switch it for a negative b. And we will get for our second equation that 1 is going to be equal to negative a plus b. And what was the a? I just left parentheses here for us to plug in what a is. A is equal to negative b. And at this point, we distribute those negatives through. We get a positive b plus another b. We get 1 equals 2b. And again, we get b equals a half. And once we have b equals a half, go back and follow the same procedure we did over here. The nice thing is, though, now I have a simpler equation. I'm going to plug it into this one. So I'm going to plug it into the one that we solved for. I can plug into either of the two original equations, or I can plug into this nice version of the equation where I've solved for one variable entirely in terms of the other. So we've already done a lot of the algebra, so this is the ideal version to pick. So plug into the thing that's triple underlined. And when we do that, I'll get that a equals negative b implies a equals negative of a half, which is negative a half. And we've found our second value. So whichever method you prefer, it'll vary from problem to problem. We're going to get the same answer both ways, or you should get the same answer both ways. Okay. After all of this, we haven't even done any calculus yet. This has all been algebra. So at this point, we've got to go back and remember, what were we trying to do? So let me go back to the beginning of this question. Our goal was to rewrite this integrand as two simpler pieces added together. So one big ugly fraction into two simpler fractions. And now I know what the a and the b need to be to make this all work. So here's the a and the b. I've solved for them down here. So what we've got is the following. Let me zoom in so I can write here. So we know essentially that 1 over 2x minus 1 times 2x plus 1, that integrand that we were dealing with, can now be more succinctly written as basically a negative 1/2, that was a, over the 2x. Let me make sure I got which one goes with which. What order did I do them in? So a went with the 2x plus 1 term. So this is over the 2x plus 1 term. And the b goes over the 2x minus 1 term. Okay. So after all of that, all we've successfully done so far, this is the partial fraction portion. We've rewritten one ugly term into two simpler terms. We've unfound the common denominator. And so we wind up with the following. Our original integral, which was the integral of 1 over 4x squared minus 1 dx, which was then rewritten as the integral of 1 over 2x plus 1 times 2x minus 1, whichever order you want to write the plus and the minus, can now be written as the integral of what we've got sitting right here. And that integral is going to be, we can put the negative 1/2 on top. I'll just keep it written kind of ugly fractions within fractions. We probably want to clean it up quickly. But we've got this. So we've got two simpler integrals. Here's 1 and here's 2. If I'd just been given this from the beginning or just this from the beginning, these are relatively quick problems. But now we have both of them to do. So let's go through and do those two. Let's evaluate the two integrals. So I'm going to start with integral 1. I'm going to pull that negative 1/2 out in front of everything just to clean it up a little bit. And this is the integral that we're working with. I want to recognize this as a u substitution because I've got a linear term basically a 2x term, and if I take the derivative of that, I'll wind up with just a constant. I can pick the constant up here to suit whatever constant I need. So what I'm going to do is I'm going to let u be equal to the entire denominator. Again, the derivative of this entire denominator will wind up just being a constant. What will that constant be? So if u is equal to 2x plus 1, then du will just be equal to 2 times dx. And I will force in a 2 up on top. And so we wind up with, let me rewrite this as a 2, and to account for that, I'm going to take the whole thing out front and multiply by another factor of a half to account for the fact that I just changed this from a 1 to a 2. So I doubled this. I need to compensate for that with a half out here. And so we wind up with this constant in front is now going to be negative a half times positive a half, so negative a fourth. And the integral that I'm going to have is basically, we can write it this way, 2dx over 2x plus 1. Switching that into being in terms of u, 2dx, our numerator, is just du, and the denominator is just u. So this is just du over u. We're going to get a natural log. And this will happen essentially on every one of these partial fractions problems. They're all going to involve natural logs. You'll almost always wind up with something that looks like this. I shouldn't say always, but almost always wind up with something that looks like this. How do we integrate du over u? Again, that's the natural log, so I'll have my negative 1/4. And this is just the natural log of the absolute value of u plus a constant of integration. I'll call it C1 because we'll have a second constant of integration for the second integral. Now we just need to convert back to the original variable, right? Our original equation wasn't in terms of u, so let's write this back in terms of x instead, the variable we were dealing with. And we get the natural log, or negative 1/4 times the natural log of the absolute value of u, which is 2x plus 1 plus c. The second integral will be done in the exact same method. So for the second integral, we've got, I'll pull that 1/2 out in front. We've got 1 over 2x minus 1 dx. Do the same thing. I'm going to let u, in this case, be equal to the whole denominator, 2x minus 1. Du will still just be 2 dx. I'm going to change the 1 into a 2 and account for that by putting another factor of a half out in front. And we will wind up with positive 1/4 this time times the integral of 2 dx over 2x minus 1, which is 1/4 times the integral of du over u. And we'll get the natural log again. We'll get 1/4 natural log of the absolute value of u plus a second constant of integration, c2. And when we plug it back in for x instead of u, we will get 1/4 times the natural log of the absolute value of 2x minus 1 plus c2. And the full answer, looking at this, is the sum of these two results, right? I need to add 1 and 2 together. So here's the result of 1. Here's the result of 2. So we get, for our final result, and we can leave the 1/4 in there, we could pull it out, but we get the integral of 1 over 4x squared minus 1 dx is equal to negative 1/4, the natural log of the absolute value of 2x plus 1, plus 1/4 times the natural log of the absolute value of 2x minus 1, plus some new constant that I'll just call c, just to be clear, where c is equal to c1 plus c2. We took two other constants and combined them into one mega constant. So just know down the line I may forget sometimes to label my constants separately, and at the end of the day they will combine into another constant. So if I called this C, and this also C, they all represent constants, but they can all in fact be different constants. Just to make things extra confusing. Okay. So, looking at this problem, what are the hard parts? What are the easy parts? Here's the whole thing. That's how much this problem takes up. Right, this is a full pager type of a problem. Once you get these down, they go a little bit faster. These integrals down here weren't bad. This wasn't too bad. It was really getting the correct guess for the form of the fractions that this was going to break into. So up here you can see that kind of tiny. Zoom in a little bit. So following those big complicated rules I wrote earlier, that's how we picked the form that we were going to guess at. And we'll look at some different forms in some other scenarios. From here, we basically, it's pretty quick. You can go through this type of, the act of finding a common denominator and then comparing the numerators. You can go through it pretty quickly to get this equation and break it down into a system of equations that looks like this. So once you've got your guess, going from this line up here down to this system of equations right here is relatively straightforward. Then we need to solve this system of equations, and this was the two different approaches. So obviously we don't need to do both approaches every time. In fact, I'm going to show you an additional approach we could have done that's kind of nice up here at this stage. It's actually nicer to do it at this line. But that's going to be the tricky part. So in all of this, the tricky parts are basically getting the correct form of a guess and then solving the linear system. That's more complicated than any of the actual integration that we did down here. Hopefully you're getting good at these U substitutions and they go quickly for you. So solving the system of linear equations and getting the initial guess, those are the two kind of tricky parts. So let me give you one other approach that can help when we're solving these systems of linear equations. So this is sort of a side note, but a worthwhile side note. We have another option that works pretty well in certain cases for solving the system of equations. Okay, so I want to go back to the line that we had up here. What was it? Sorry, to have to do this a million times. Basically, I want to go back to this line right here. Our system of equations before we wrote it as two clear, distinct, separate equations. So I want to look at this line. That's all I'm trying to copy down. So it's a times 2x minus 1 plus b times 2x plus 1. So this is what we're trying to solve, right? If we can solve what a and b are, we're basically ready to start doing our integration. We're right there. This equation needs to hold true for every single value of x that you could pick. So the way we did it before is we broke it into different parts. We broke all the constants as one equation and everything that was proportional to x as a second equation. That is an option. But the other one is to recognize that this equation needs to hold true for every single possible value of x. It's essentially an identity, right? This is an identity, meaning it's true for all values of x. We want to pick an x or two that make it easy. If it's true for all x, that means it's also true for convenient values of x. So let's pick some convenient values of x. To plug into this thing. And what do I mean by convenient? Well, if I were to pick, for example, x to be 1/2, if I plugged in x equals 1/2 right here, I'd get 2 times 1/2, which would be 1. Then I'd subtract off this 1, and I would get 0. And this entire term would disappear. Basically, I found the solution, or the 0, of this linear factor right here. I found it 0. And by doing that, it killed off this entire piece, and I would have an equation that was only for b. Similarly, if I picked x equals -1/2, I could kill off this entire term. I could get rid of all the b's that show up and have an equation just for a. This will work. This approach, picking convenient values of x, works when we've got these nice linear factors that we're dealing with here. It won't work, and especially for multiplicity 1, but it'll work for higher multiplicities. It just doesn't work very well for those quadratic factors, but it works pretty well when we've got these nice linear factors like this. So, for example, if we let x be equal to 1/2, what does our equation become? It becomes 1 is equal to a times 2 times 1/2 minus 1 plus b times 2 times 1/2 plus 1. And this becomes 1, this whole thing becomes 0, and we wind up with just getting 1 is equal to, the a term is entirely gone. This term will simplify. Again, this is a 1. I'm going to add it to the other one, and we'll get 2. So 1 is equal to 2b. And from there, solving for b, we get that b is equal to 1/2. Same thing we got before. And if I pick the other convenient value, x equals -1/2, and plug that one in, we'll get 1 is equal to a times, again, just plugging in -1/2. So 2 times -1/2 minus 1 plus b times 2 times -1/2 plus 1. So all I'm doing is plugging in -1/2 where these two x's go. And when we do that, this will give me -1, this will give me -1, this whole piece becomes 0, and the b terms disappear, and this whole piece becomes -2. -1 minus another 1 is -2. And we wind up with simply 1 is equal to -2a. And if we solve for a, we get that a is equal to -1/2. And these, we'll hopefully recall, are the exact same values that we got up here. So this is another approach to get the same results that we got, another approach for solving these linear equations. And you can actually use a combination of these. You can do this approach, which is very convenient for these linear terms, and if there were still quadratic terms, once you've solved for some of the values of a and or b up here, you can plug those in and do the rest of the problem with either the substitution or the elimination method. You can just plug in, well, I already found that b was equal to 1/2, let me just replace all the b's that show up everywhere with 1/2, and now I'll have an easier way to solve for what a is. And you can use a combination of both techniques. But again, this works best for distinct linear factors, meaning, multiplicity 1 it works best for. But you can use a combination. If there's higher multiplicities, you can still use it sometimes and kind of use a combination of different approaches. But this is the best approach, or the best scenario for you to use this approach in, rather. Okay, so I went through this example hopefully slowly enough and carefully enough that you're bored out of your mind. Let me go through the next example a little bit more quickly, hopefully, and we'll see how this will work. So let's do another example. You can see I'm starting to tilt in my writing. Okay. Let me just copy this down here. I want the integral of 5x squared minus 3x plus 1 as our numerator over x cubed minus 2x squared plus x minus 2 dx. So again, notice the numerator is of a lower order, it's a quadratic, than the denominator, which is a cubic. If it was higher, you could just do some sort of either polynomial long division or polynomial synthetic division, depending on how bad the bottom looked, to try to simplify things, and you might wind up with just an easy polynomial to integrate, doing it that way. But in this case, the denominator is a higher order than the numerator. This is a partial fraction problem for sure. So I want to factor the denominator. That's always our first step. Factor the denominator. And this one looks scary. I never like factoring cubics. Quadratics are not bad. I know how to factor quadratics. But cubics are a little scarier. But luckily, this one can be factored by grouping. And I can kind of notice that if I look at the first two terms and the last two terms, they kind of have a similar pattern. They both have the same negative sign, and they both have a 2. So a term with only x's minus 2 times a term with x's. A term with only x's minus 2 times a term. You could think of this as an x to the 0th power term with only x's. So we're going to factor this one by grouping. And again, if nothing else, this will just be a callback to intermediate algebra, which you probably took a very long time ago. Different factoring techniques. So this one, I will basically say I'm going to group the x cubed minus 2x squared group as one group, plus the x minus 2 group as the other group. So group the first two together and the second two together. And now I'm just going to factor as much as I can out of here. These both have at least an x squared in them, so I'm going to factor an x squared out. And I'll be left with an x minus 2, which is great, because over here I've really got a 1 times x minus 2. And now we can factor the x minus 2 out of both of these to get x minus 2 times x squared plus 1. And this is a quadratic term. It is not a difference of two perfect squares. It is a sum of two perfect squares, so there's nothing we're going to be able to do. We're not doing imaginary numbers as our roots or anything like that. So this is as factored as this is going to get. And you'll notice we have one linear term of multiplicity 1 and one quadratic term also of multiplicity 1. So now we're going to have to guess the following. So we get, again, all I'm trying to do is replace that integrand. Here's that integrand. Let me leave it on the page so I can see it while I write it down. So I want to rewrite 5x squared minus 3x plus 1 over this big cubic. And heck, let's write the factored version of the cubic, seeing as how we just did all that work anyways. So here is our integrand with the denominator factored, and I want to write it instead as a sum of two different pieces in this case. So, So I want to write it as something over x minus 2 plus something over x squared plus 1. And if we go back up to those rules, this term is linear. All we need to guess as the numerator for a linear is a constant. But this term is quadratic, and we can't get away with just guessing a constant up here. And one way to think about it is if you look at this, effectively, this thing looks essentially like a 1 over x, or in this case 5 over x. But if you compare the highest power on top to the highest power on the bottom, the highest power on top is 1 less than the highest power on the bottom. And down here, you'll notice the power on top is 1 less than the power on the bottom. Here it's x to the first power. Here this is a constant, so you could think of that as x to the 0th power. Similarly, I want to do the same thing here. X squared plus 1, I need to have something up here that's 1 power less. So it's going to be b times x plus potentially a c. So we need to guess a linear term on top of this. And again, just to remind you where I'm getting these, it comes back to our rules that we had right up here. If our denominator is linear, we just guess constants on top. If our denominator is quadratic, we guess lines on top. If the multiplicity is just 1, we can ignore all these other pieces. And the example I'll do after this, we'll do an example where we have something with a higher multiplicity, with a multiplicity that is bigger than 1, and we'll see how to deal with that. But for now, both of these are just a multiplicity 1. That's why we guess a constant over the linear terms, and we guess a line over the quadratic terms. It's from those rules. And again, the intuition is kind of what I mentioned a minute ago. We're trying to compare it to this thing, and essentially the idea is that power on top is smaller than the power on bottom by 1 in this case. One way you can kind of think of that. So now we would find a common denominator over here and use that to try to get an equivalent form. So basically, if I found a common denominator here, what would it look like? So I would need to multiply this term by this denominator top and bottom, and I'd need to multiply this whole thing by this denominator top and bottom. And I would get a times x squared plus 1 plus bx plus c times x minus 2 over x minus 2 times x squared plus 1. So again, all I've done is multiply this one top and bottom by this denominator, multiply this term top and bottom by this denominator to get a common denominator. Same approach. And you'll notice I'm comparing this to this. They have the same denominator, so for them to be equivalent, they just need to have the same numerators. So we're going to just compare the numerators. So if we compare the numerators, we wind up with 5x squared minus 3x plus 1 is equal to a times x squared plus 1 plus bx plus c times x minus 2. And we can do a couple of things. We have essentially our linear system. If we were to break it down and look at the constant terms, the terms that are proportional to x and the terms that are proportional to x squared, we would wind up with 3 equations for our 3 unknowns, right? We have a, b, and c. So 3 unknowns, we need 3 equations, and we get them by looking at the constants separately from the linear terms, separate from the quadratic terms. So that's one approach. Or we can use, for at least the linear term, there is at least one number I could plug in that would make this nice. And that's the number x equals 2. If I plug in x equals 2, it's going to kill off this whole piece. It's going to kill off both the b and the c term, and I'll wind up with an easy equation to solve for a. Then once we have a, we can go back and try to plug in and solve for b and c. So we can use a combination of approaches. So that's what I'm going to do. I'm going to start with, in my approach, I'm going to pick an easy value. So I'm going to say, let's say I want x to be equal to 2. Again, how did I pick x equals 2? I wanted to find a convenient value I could plug into this that would kill off some of the terms. And 2 makes this piece 0, and it's going to kill off this whole chunk of terms here. So on the left-hand side, I'd get 5 times 2 squared minus 3 times 2 plus 1, and that's going to be equal to a times 2 squared plus 1 plus, I'll write it out and then we'll cancel it, bx plus c times 2 minus 2, which again, that is 0, and that means this whole term disappears. And we wind up with, on the left-hand side, 2 squared is going to be 4. 4 times 5 is 20, so I'm going to have 20 minus 3 times 2 is 6 plus 1. And on this side, I'll have 2 squared, which is 4, plus 1, which is 5, times a. And so over here, I'll take the minus 6 and then plus 1, and we will get 15 equals 5a, which tells me that a must be equal to 3. And now that I know that a is equal to 3, we can go try to solve for the remaining equations. So we can plug in to basically breaking this down into looking at the different orders, so to speak. So I'm going to look at the order 1 terms, the order x terms, and the order x squared terms in that equation. And we already have a, so it's going to make life a lot easier as we plug stuff in. We're not going to have 3 equations for 3 unknowns. We'll only have 2 equations for 2 unknowns because we already found one of our unknowns. So the order 1 terms, when I look at this, I'm just looking at the constants. And on the left, the constant is 1. And on the right, I will have a times 1, so I'll have a, which we will plug in just a moment, as being 3. And over here, when I FOIL this term up here, so just note that just this piece by itself, if I were to, if I FOIL this piece out, we'll get bx squared. We'll get minus 2bx plus cx, so minus 2bx plus cx, and then I'll get minus 2c. So I get a, and the only other constant that I wind up with is minus 2c, this piece over here. Okay, so I have a, which is the constant that comes from this, and minus 2c, which is the only constant that comes from this FOIL. But we already found a as being 3, so I really have 1 is equal to 3 minus 2c, and we can solve that. So all I need to do is subtract 3 from both sides, and I'll have negative 2 equals negative 2c, which tells me that c must be equal to 1. Now we'll look at the order x terms. And we'll only do these other ones if they're necessary. Once we've got A, B, and C, we're good. And so I have A and C. I just need an equation that involves B now. I already know A and C, and we're good. So I just need an equation where the B survives. So I'm looking at the order x terms. On this side, I have a negative 3x. So I'm just going to write the negative 3 that multiplies that x. And on the other side, this doesn't give me any x terms, right? Ax squared or a gives me an x squared term and a constant term, but no x terms. And this one over here, we already FOILed it out. It gives me these 2 terms that are proportional to x. So on the other side, I'm just going to get a minus 2b times x plus a c times x. And so these are all the linear terms that survive from this equation. They're the linear terms. Or sorry, yes, the linear terms, the x to the first power terms. But I already found what c is. We just found that c was equal to 1. So this is really going to say negative 3 is equal to negative 2b plus 1. And I can subtract 1 from both sides. And once I've subtracted 1 from both sides, I'll have negative 4 is equal to negative 2b. Divide both sides by negative 2, and we will get that b is equal to 2. And so now I've got all of my constants. There's A, there's C, and there's B. And this one turned out to be unnecessary. And why is it unnecessary? It's unnecessary because we used this approach, plugging in a convenient value to find one of our numbers. So I had already used 3 equations. Here's equation 1, 2, and 3. So instead of having these be the 3 equations for my 3 unknowns, I used this equation as my first equation, and then just 2 more down here to get my total of 3 equations for my 3 unknowns. So we don't even need that order x squared one. We're good to go. Okay, so we've got our a, b, and c, and our integral becomes the following. So our integral becomes Let me just go back. I have it written down here. Hopefully you have it written down as well. So it was 5x squared minus 3x plus 1 over x cubed minus 2x squared plus x minus 2 dx. We were able to factor the denominator and get this to be the integral of 5x squared minus 3x plus 1. You don't need to write all these steps when you're doing this on an exam or on homework. I'm just trying to be sort of a completist here and not skip anything so people don't get lost. So the next thing we did was factor the denominator, which gave us x minus 2 times x squared plus 1 dx. And now we've finally solved for a, b, and c to get the integral of our first term. Let me zoom out just enough so we can see all of this on one line. There we go. Right. Here's what we've got right here. We're taking the integral of this. I now know a, b, and c, so I'm going to write this form in. So it's the integral of a over x minus 2. A was 3, so 3 over x minus 2 dx, plus second integral, which is the integral of bx plus c. So bx plus c will be 2x plus 1 over x squared plus 1 dx. Okay. So here are our two integrals. How are we going to deal with these? And I could even split this one up if we wanted to into a third integral, and that might even be the easiest thing to do. So let me just write that out one more time. Integral of 3 over x minus 2 dx plus the integral of 2x over x squared plus 1 dx. And lastly, I'm going to take care of the plus 1 we had in the numerator to get an additional integral of just 1 over x squared plus 1 dx. Okay. This one is going to be a u substitution. This one's going to be a u substitution. And this one is either one that you just know off the top of your head, or it turns out to be a trig substitution, which I'm not going to go through that part, but you may recognize this as being an arctangent. Hopefully you recognize that. It may take a while, but this is a trig substitution one. Notice the reasoning for that is the derivative of this down here is going to be 2x. I don't have an x to play with to make this a u substitution. So there's my indication. I've got some sort of thing that looks like, essentially you could think of it as x squared plus 1 quantity squared. I've got one of these terms raised to some power, and I don't have what I would need to make it a u substitution. So this is going to be a trig substitution. So a u sub, and a trig sub. Okay, so let me label them all 1, 2, and 3, and let's go ahead and do them all. Maybe I will do that trig sub after all, just get a little extra practice in here. So for the first integral, I just have the integral of, I'm going to pull that 3 out and write it as 3 times the integral of 1 over x minus 2 dx. And I'm going to let u be equal to x minus 2. du is simply going to be dx. And this whole thing becomes 3 times the integral of du over u. And that's going to be 3 natural log of the absolute value of u. I'm going to forget about the plus c's until the very end, so just keep that in mind. I'm not going to write the plus c here. We'll just add that in at the very end of this problem. And that is 3 times the natural log of the absolute value of x minus 2. So there's that portion. The second portion is similarly easy, and it's very convenient. I even have the factor of 2 that I needed already. So I'm going to have the integral of 2x over x squared plus 1 dx. I'm going to let u be the whole denominator. And that means that du, the derivative, will be 2x dx, which is exactly what we've got. So this whole thing just becomes the integral of u over du, du over u, which is going to be the natural log of the absolute value of u. But what is our u in this case? It's a different u than the one we used before. Natural log of the absolute value of, in this case, x squared plus 1. Again, I'm not going to write the plus c. We'll add that in at the end. And the last one is that trig sub problem, or recognizing it as an arctan. It's the integral of 1 over x squared dx. We'll draw our triangle. Put in my theta. The term that I'm interested in is trying to rewrite this in terms of theta. That length is going to be the one that shows up on the hypotenuse. So this length is going to be the square root of x squared plus 1. I'm going to put my x over here and my 1 over here then. So here's my triangle. This squared plus this squared will indeed be equal to this squared. And I can rewrite a couple of things. So for example, we get that in this case, cosine of theta is going to be equal to 1 over the square root of x squared plus 1, right? Adjacent over hypotenuse, we get that if I do the tangent of theta, we will get, in that case, x over 1. And so we've got, and this tells me that then our dx can involve the arctangent, so if x is equal to tangent, then it's going to involve the secant squared. Here we go. So take the derivative of both sides. The derivative of tangent is going to be secant squared of theta d theta. And let's see, this piece also implies, right, we don't actually have the square root up here, so I have to square this whole thing to get it to look like that. So this piece implies that cosine squared of theta is going to be the integrand that I actually wanted, which was x squared plus 1 over x squared plus 1. So there's all the pieces. And we now get that the integral that we are starting with here is going to be cosine squared of theta, right? That's this part, times dx, which is secant squared of theta, d theta. And that may look scary at first glance, but hopefully you recognize very quickly that let's just rewrite secant in terms of cosine and see what cancellation we can get. So I've got cosine squared of theta. What is secant? Secant is 1 over cosine, so I also have 1 over cosine squared of theta. And I'm multiplying them together times d theta. They are going to cancel, and I just have the integral of d theta, which is equal to theta. Great. Here's my answer, again, plus c, which I will leave off until we put the full answer together, but I'm not in terms of the correct variable. So how do I get this in terms of the correct variable? Well, we can do that right here. So we need to, for theta in terms of x, we want to get theta in terms of x back in the original form. So we know that the tangent of theta is equal to x according to this line right here. And therefore, if I take the arctangent of both sides, we will get theta is equal to the arctangent of x. Okay, so there's solving. Whoa. There is solving the last integral. Putting all three together, we get our final answer, which is going to be that original, oh, come on, stop zooming. We get that our integral is going to be equal to, I'm not going to recopy that whole integral. That you know what the original integral was. But our answer is going to be, it was 3 times the natural log of the absolute value of x minus 2 plus the natural log of the absolute value of x squared plus 1 plus this theta piece, which is the arctangent of x, and finally plus c. So there's the answer to that problem. Let's do one last example before I put you all to sleep. Let's try this one. I want to do the integral of x cubed plus 2x squared plus 2x over x squared plus 1 quantity squared dx. Well, the nice thing is the denominator is already factored for us, right? I'm not going to be able to clean this denominator up anymore, but the bad news is it's a quadratic term and it's of multiplicity 2. It shows up twice. So let me just write that here. Quadratic of multiplicity 2. So what that means is if I'm going to rewrite this thing, it's already factored, but if we want to rewrite it, we're going to have x cubed plus 2x squared plus 2x over x squared plus 1 quantity squared, that's going to be equal to something over the x squared plus 1 to the first power plus something else over x squared plus 1 to the second power. This was our rule. And what goes on top, because they're quadratic, is going to be linear guesses in both cases. So ax plus b, cx plus d. And unfortunately, that's 4 unknowns. So where did I get this form from? Let's go back up and check our rules. But the idea is because of the multiplicity being greater, so if this had been a multiplicity 1, I would only need to guess this one term. But because it was multiplicity 2, we do this term to the first power and this term to the second power. If it was multiplicity 3, if I had a cubed here, we'd have to have this term, plus a third term where we had a cube instead of a square, and we'd have ex plus f, and we'd have 6 unknowns, and it would be even worse. But this rule came from way, way back. Okay, maybe I do want to zoom out now. Way back, here's our rules, so long ago. Here is our rules. For each quadratic factor of the form ax squared plus bx plus c, so in our case it's what, x squared plus 1, to the nth power, in our case n is 2, the partial fraction decomposition must include all of these terms. So we needed to include this term plus this term because n is 2 in our case. So here are the two terms that we included down below. The denominators are just, there is no linear term in there, so it's just x squared plus 1, whole thing squared, and on top we just guessed 2 lines, ax plus b, cx plus d. You could, again, use subscripts if you prefer, but I really don't tend to use subscripts until I've got more than maybe like, I don't want to exhaust the alphabet, so maybe after I've got more than like 6 unknowns, I'll do A, B, C, D, E, and F. I'd probably even still go with G and H after that, and then maybe I'd start considering using subscripts. Hopefully you don't have any systems where you've got to solve 8 unknowns, but in this case we're going to have 4. Okay. So hopefully this form of what we're guessing makes sense. If you guess the wrong form, generally what will happen is you will wind up with a contradiction. When you try to force equivalence by finding the common denominator over here and getting it set equal to this, you'll find some sort of contradiction as you start doing your solving your linear system. You'll basically find something that cannot work. You'll literally wind up with something that says like 1 equals 2, and it will fall apart. If you wind up with that as you're solving your linear system, something where you get a contradiction, something that clearly cannot be equal to the other thing, 1 equals 2, 4 equals 0, whatever the case may be, it means in all likelihood either you made a dumb algebra mistake somewhere or you guessed the wrong form to start off with. So make sure you guess the right form. If you screw up on the form, everything's going to go south quickly. Okay. So I want to get a common denominator for these. The common denominator, this already has the correct denominator. It's the same as this. I just need this denominator to be another x squared plus 1. So I need to multiply this term by x squared plus 1 top and bottom. And we would get ax plus b times x squared plus 1 plus cx plus d, in parentheses as well, all over x squared plus 1, whole thing squared. So again, this term was already correct. It hasn't changed. But this term, this power went up, so I needed to compensate for that with an extra x squared plus 1 in the numerator here. And now these two things must be equivalent. They already have the same denominators, and that must mean that the numerators must be the same. So let's just simply compare numerators. I don't know what word I'm writing there. Numerators. And when we compare numerators, I'll get x cubed plus 2x squared plus 2x is equal to, in this case, ax plus b times x squared plus 1 plus cx plus d. Okay, here's 4 unknowns, a, b, c, and d, and what looks like only one equation, but it really must be 4 equations, and indeed we'll see that it is. The constants must all be equal, the linear terms must all be equal, the quadratic terms must all be equal, and the cubic terms must all be equal. Okay. Notice that when we have one of these repeated quadratic roots like this, there isn't a nice value of x I can plug in over here that'll kill stuff off, right? This one would be nice if we could figure out a way to kill this term off, but the only number that I could plug in here would be I, the imaginary number, because I squared would give me the -1. I'd need to cancel this. That's not an option. We're not plugging in i's, okay? So we want to keep all our values real, no imaginaries. Our method that I suggested earlier, where you maybe find a convenient value and plug it in, there are no convenient values. So that means we have to do the comparison order by order. So we're going to have to break this down into the order 1 terms, the order x terms, order x squared, order x cubed. Because of that, I want to actually right now this is factored. I want to FOIL it all out because I want to actually see all the terms individually. So I'm going to FOIL this out and expand this whole right-hand side since we're not going to be able to find a nice number to plug in. If we could find a number to plug in, by all means, leave it factored. It'll be easier to evaluate if it's already factored and we're plugging in a convenient value that'll kill stuff off. But right now there are no values, so we're going to just have to FOIL it all out. When I FOIL these two terms, I'll get ax cubed plus ax plus bx squared plus b plus cx plus d. So there's the right-hand side. And it must be equivalent to the left-hand side. So let's compare one term at a time. I'm going to look at all the order 1 terms, then all the order x terms, then all the order x squared terms, and lastly all the order x cubed terms. And these will give me my 4 equations for what are now my 4 unknowns. So looking at the constants, what constant do I have on the left? Well, all these have x. The constant is 0. You can think of a plus 0 here. So we don't have any constants on the left. We have 0. What do we have on the right? Well, as we go through these, this is a constant, the b, and this is a constant, the d. So the only constants we wind up with over here are b plus d. And that's nice. It doesn't let me solve for b or d, but it does tell me that if I solve for one in terms of the other, they're going to have to be opposites, because when I add them together, they're going to cancel and give me 0. So whatever I find for b, d must just immediately be the opposite of that, or vice versa. Now we'll look at the linear terms. So on the left, it's 2. I have 2 x's. And on the right, as I go through this, right, cubic, but here's a linear term, so I'll have a times x, and then I have a second one, which is plus c. So those are all of my linear terms. So let me kind of cross them out. We've taken care of, at first, you could think of the plus 0 over here. We've used that with that and that the first time. We did this one, and this one so far. Just make sure that we're using them all up. Now let's do the order x squared. I have 2x squared on the left, right? 2x squared on the left, and on the right I just have bx squared. So there's just a b on the right hand side. We've killed off that term now. And finally, and this term. And finally, for the x cubes, I have 1x cubed on the left, and I have ax cubed on the right. Well, that's really nice. These last two equations immediately give us 2 of the values that we need. So this one again, hopefully it's obvious. A equals 1, b equals 2. Once I know that b equals 2, what does this one tell me? This one told me that b is equal to negative d, or maybe it's, let me solve it the other way around. It might be easier for us. So d is equal to negative b. They're opposites, we said. And that tells me immediately that now d must be equal to, because I already found b is equal to 2, d must be negative 2. And the last one, I have that a plus c equals 2, but I know what a is. So this one gives me 2 equals a plus c, but a is 1, so 1 plus c. Subtract 1 from both sides, and what do we get for c? C is equal to 1. Okay, so there are all of the values, and our integral becomes just zoom out enough so I have room to write. So we're trying to do this integral, x cubed plus 2x squared plus 2x over x squared plus 1 quantity squared dx. And it becomes this, what I've got written right here, with now these values for a, b, c, and d. So we're going to get ax plus b, which is going to be, a is 1, so x, 1x plus b, b is 2, so x plus 2 over x squared plus 1 dx. That is this piece now accounted for. And now let's account for this one, cx plus d. So c is 1, so 1x plus d is going to be minus 2. So this one we get the integral of x minus 2 over x squared plus 1 quantity squared dx. Okay, so this looks ugly, and it is ugly, but I'm going to break this up into 4 separate integrals now. I'm going to treat basically the a, b, c, and d, all 4 different pieces of the numerator totally separately. Let's break it into 4 separate integrals and treat each one of those integrals separately. So this is going to be equivalent to, zooming back in a little bit here. So I'm going to get, the first integral is going to be just that x over x squared plus 1 dx. The second one I will get 2 over x squared plus 1 dx. So now I've taken into account this part and this part. Now let's move over to this one, plus the integral of x over x squared plus 1 squared dx. And lastly, this minus 2 piece. So plus, or let's pull the minus out, minus the integral of 2 over x squared plus 1 squared dx. And label 1, 2, 3, and 4. Here's our 4 separate integrals that we're going to deal with. Go through them real quickly and let's see if you can figure out, before I do it, let me pause for just a minute. What technique are we going to need for this? That one is a U substitution, right? The numerator, x, is basically proportional to the derivative of the denominator. So x squared plus 1 has a derivative of 2x. I've got the x I need right here. I just need to put a factor of 2 in front of it. This one over here, we don't have the x that we need on top. This one is going to be a trig substitution, but it's the exact same trig substitution we did in the last problem. It just has a factor of 2 in front of it. So it's going to be 2 times the arctangent of x. So this is arctangent. What about this one? This one we're going to be able to do with the U substitution as well. It's just going to be a little bit more complicated. We're not going to get a natural log out of it. This one, if I make U the same thing, x squared plus 1, I do have what I need for my du here. But it's not going to give me du over u, it's going to give me a du over u squared. And we'll have to deal with that integral. And this one over here is yet another trig substitution. So 2 trig subs, 2 u subs. Okay. Integral 1. I'm going to let u be equal to the denominator. That means that du is going to be 2x dx. I'm going to sneak that 2 back in over here and account for it with a factor of 1/2 in front of everything. And this thing will be 1/2 times the integral of du over u. And we'll get 1/2 times the natural log of the absolute value of u. Again, I'll leave off the plus c for now. We get 1/2 the natural log of the absolute value of x squared plus 1. Okay, one integral down. Second integral, we just said if I pull that 2 out in front, this is the integral 1 over x squared plus 1 dx. We just did that. In the previous example. It's equal to, in this case, that factor of 2 times the arctangent of x. So if you want to see that, you can go back up to this part right here. Right. The only difference is we have a factor of 2 out in front of everything now. Okay. So there was the second one. What is the third one? Third one is x on top. So we've got the integral of x over x squared plus 1 whole thing squared dx. I'm going to make the same substitution. I'm going to let u be equal to x squared plus 1. du is going to be 2x dx. I'm going to force a 2 there and account for it with a 1/2 in front of everything. And this becomes 1/2 times the integral of, here's my 2x dx, there's my du on top. And on the bottom, I don't just have u, I have u squared. Which you can think of as just 1/2 times the integral of u, because it's on the denominator. This is just u to the negative 2 du. And we can integrate that using just power rule. So it goes up by a power of 1. So what's 1 more than negative 2? It's going to be negative 1. And then we just need to think of what's the correct factor. So if I were to take the derivative of u to the negative 1, I'd get negative u to the negative 2. I don't want that negative sign here, so I need an extra factor of negative sign. to account for that. And that winds up being negative 1/2 u, which is x squared plus 1 to the negative 1. Or we could rewrite that as, whole thing as, what are we going to get? 1 over, let's call it negative 1 over 2 times x squared plus 1. And again, plus c. So that's what that one will look like. And the last one, which is the integral of, we can't forget, don't forget this minus sign when we are combining all of these at the end, but it's 2 over, and in fact, let's pull that 2 out. All right, it is 1 over x squared plus 1 squared dx. Okay, this is going to be a trig substitution. You can honestly just look this one up in a table if you needed to as well. But let's give this one a shot. It's going to be, so we'll draw my triangle. It's going to be the same triangle we drew for the previous one. Here's my square root of x squared plus 1. Here's x, here's 1. And it's going to be the same substitutions we made in that last one. So I'll notice that I'll notice, for example, that cosine of theta is equal to 1 over the square root of x squared plus 1. If I want this term here, where it's x squared plus 1 quantity squared, I need to take this to the 4th. So take both sides to the 4th power, and that'll give me the integrand that we currently have over here. And similarly, if I take the tangent of theta, I can get what x is, and that tells me that x is going to, dx is going to be secant squared of theta, d theta. And that gives me the pieces that we need. Our integral is, got that factor of 2, don't want to forget that, times the integral of dx, so dx times this piece. Here's this piece, here's dx, it's going to be the product of those two pieces. So cosine to the 4th of theta, secant squared of theta, d theta. This piece, again, remembering that this is, secant is 1 over cosine, will basically cancellation of sum of the cosines. So this is going to be 2 times cosine to the 4th of theta times 1 over cosine squared of theta d theta, and we'll be able to cancel this with 2 of the powers and be left with a cosine squared. So we've got to integrate 2 times the integral of cosine squared of theta d theta. How do we deal with this piece? How do you integrate cosine squared? We need to go all the way back to our trig integrals from a couple sections back. This requires the power reduction formula. So this is going to be equivalent to 2 times the integral of cosine squared simplifies to 1/2 plus cosine of 2 theta over 2 d theta. Luckily, the 2 here is going to cancel with both of the 2's down there, and we're just integrating 1 d theta, so just d theta, plus the integral of cosine of 2 theta d theta. Okay, this piece right here is going to just be theta, and this piece technically requires a u substitution, but I'm going to kind of see if we can do that in our head. So I'm going to get theta plus, what is the u substitution? I know it's going to be some sort of sine 2 theta, because when I take the derivative of sine of stuff, I'm going to get cosine of that same stuff times the derivative of the stuff. This would give me an extra factor of 2 that I don't want. So to account for that, I need a factor of 1/2 right there. Okay, so here's our answer, but again, this answer is in terms of theta. We need to go back and write everything in terms of x, and we can do that. Theta is going to be that arctangent term, so we'll get an arctangent out of this piece, and the sine of 2 theta, we can use the double angle formula, or we can just write it as sine of 2 times the arctangent of theta. It's going to be a big ugly mess, but maybe that's fine in this case. So theta, we just said we would solve for at this stage right here, take the arctangent of both sides, and we'd get that theta is equal to the arctangent of x. So this is going to be we're going to get the arctangent of x plus a half times the sine of 2 times the arctangent of x. And that's fine. It's ugly. It's possible to simplify this. You can use the double angle formula and write sine of 2 theta. I want to say it's 2 sine theta cosine theta. And you could go up here and find what sine of theta and cosine theta are on this and multiply them together and get some simplification. And in fact, we can do that. I think you wind up with like a, out of this whole piece, and I've forgotten this whole time. No, I canceled the 2's. We're good. But I'm just going to leave it like this. It's good enough. Okay. And our final answer is these 4 pieces all put together plus c. So we get oh, I'm writing in rainbow colors. So we get, the first one was 1/2 log of absolute value of x squared plus 1. The second one was 2 arctangent inverse, or yeah, 2 arctangent of x. Then we had, where's the third one? Minus 1 over 2x squared plus 1. And for the last piece, we had to subtract this. Remember, it was a minus sign here, so it's going to be minus an arctangent of x and minus another 1/2 times the sine of 2 times the tangent inverse of x plus c. So obviously simplify these a bit. These 2 pieces are like terms. We'll actually wind up with only one arctangent. And this piece over here will wind up, I want to say this is going to wind up giving us, looking at what we had up there, I think this is going to wind up giving us something that involves like an x over x squared plus 1. Something in that ballpark based on, right, we can write the double angle formula right here. We could rewrite sine of 2 theta as 2 sine theta cosine of theta, and then come back up here. Sine of theta will be x over the square root, cosine theta will be 1 over that square root, and when I multiply them together, the 2 will cancel this 1/2, so this 1/2 will disappear, we won't have that, and we will get x over this times 1 over this, the numerator will be x, the denominator will be this squared, and we will indeed get exactly what I've got here. So this will give us basically a factor of 2. I really need to extend that all the way out there. We'll cancel with that 1/2. So the book answer would probably be this. If you were trying to do this in the book. Oops. I had to cancel one of these, so plus tangent inverse of x minus 1 over 2x squared plus 1. And this last one, I'll have that minus sign, x over x squared plus 1. And what am I doing now? Plus c. There's our final answer. Just know, like, keep in mind, when it comes time for the exams, don't be freaking out too much. Obviously, I can't really give you a problem like this on an exam unless it's a one-problem exam. So just keep that type of thing in mind. The problems you're going to get on the exams can only be so bad, right? They can't be as bad as this. Or maybe it's get to the point that you get to here and then don't actually evaluate any of the integrals or something like that. So just keep in mind, these problems are tedious. They take a long time. I've trimmed many of them from the homework, so hopefully it doesn't take you forever. But this is what we're looking at. So good luck on these.